Hello, everybody, and welcome to lesson 6.3, which is on page 358, and it's about proving that triangles are similar. If you remember from our previous lesson, similar means it's not exactly alike, but it has the same shape, the triangle in this case, and the symbol is this little tilde, so that symbol is the sign for similar. And today you're going to pay special attention to use the AA, the SAS, and the SSS similarity theorems. We have already learned about congruency theorems that look exactly like these two, but this time it's about being similar. So the little squiggly right here makes that difference. And AA just means two angles. And I'll show you what all these mean. So there's three sections you need to pay attention to when you do your homework. Okay, and we're also going to talk about indirect measurement, which is really interesting, to me at least. On the bottom, we're starting with the AA similarity postulate. So what that says is if you have two triangles, then all you need is two angles that are equal for the two triangles to be similar. So you need two angles. And the reason is the third angle is by default equal, because remember, if two angles are equal, the third one is by default. So minimum is always the rule in math. So really you could say, oh, I'd like to have three angles that are equal, but the minimum is two. Okay, so that means these two triangles are similar. Okay, let's read that. If two angles of one triangle are congruent to the two angles of another triangle, then the triangles are similar. You can show that two triangles are similar when you know the relationships between only two of three pairs of corresponding parts. Remember, corresponding means in the same location. So we're going to make sure we look at that. This is the AA similarity postulate. Okay, so that's the first one. And we're moving on to page, well, I missed one. Page 369 is over here. This is 359, I apologize. We're going to the top. We're going to use the AA similarity postulate, okay? And the question is, are the two triangles similar? How do you know? So I'm looking to see if I can find two angles that are equal or congruent. I only see one so far, that's the 290. So I need one more. So what I'm going to do is find the third angle, because the third angle will give it away. If that's 39, then I will say yes. If that is not 39, then it's no, okay? So how do I find the third angle? I add 2. And then I subtract the sum from 180. And that's 39. So there, this works. So notice these two are equal and these two are equal. So I'm going to answer yes. They are similar. By the AA similarity postulate. Okay, and then over here on the plan, I always like these plan. Circle it, highlight it. What do you need to show that the triangles are similar? You need to show that at least two angles are congruent. There's our symbols, right? But in this case, I had to find the third one. In this case. Okay. Okay, on this page, we're done. Now go to the next page. And on that one, we have several ideas. So this is the side angle side similarity theorem. So here, that gets a little more complicated. The AA is the simple one. This one, okay, let's read. If an angle of one triangle, there's my one triangle, is congruent to, they call it an angle, I say one angle. So there's only one angle involved. And the sides that include the two angles are proportional. So the sides that include those two angles are these two. The word include also could say the sides that form those angles, form. If they're proportional, remember when they're proportional, you have two equal fractions. So let's see, then the triangles are similar. So this side, AB, this one, over this side, QR, has to equal AC over QS. And this is the correct proportion, yeah? And those two angles have to be equal, then the two triangles are similar. So this one is a little difficult. The last one, SSS, is not that hard. We're going to just compare the ratio of each corresponding side. If the corresponding sides of two triangles are proportional, then the triangles are similar. So AB is, so you start anywhere, call it AB over QR. Yeah, that's my first ratio, is equal to AC over QS. They have to be in the same location. You can't just willy-nilly set up proportions. BC is over RS. This is called an extended proportion because you got three. Yeah, if you have two, that's normal, but three or more is called extended proportion. And if these values are the same, then you have two similar triangles. All right, so let's review. We have AA, we have SAS, and we have SSS. All right, so that's the main ideas, three of them that you have to constantly go back and forth to. Now let's look at, where are we? Page 361 top, verifying or making sure triangles are similar, verifying triangle similarity. Are the triangles similar? That's the question. So the answer should be a yes or no. If so, if yes, write the similarity statement, which I'll show you for the triangles, and explain how you know the triangles are similar. So that would be, you could say, oh, by AA, or SAS, or side, side, side similarity. Okay, those are the choices. That's why they ask you that at the end. Okay, so we got two triangles. So these look like we have no angles, and therefore I'm heading for SSS, which we have three sides. So I'm going to set up an extended proportion. How can you make it easier to identify corresponding sides and angles? I can see, how about if I flip this triangle up, then that would be 12 and that would be 8. Flip up the second triangle. Sometimes we can turn things around to make it match better. So I'm now using this one, okay? So let's look. AB corresponds to this. So 9 and 12 correspond. So I'm going to set up that proportion. And that equals, then this side would be the same as this side. But remember, I started with a smaller one, so I got to start with the smaller one again. I cannot mix and match. And then the third side, the smaller one over the third side on the larger one. So you can kind of think smaller over larger. And you have to keep that straight. You could use the other way around as well. You could start with the larger, but as long as you keep it in the same order, you're fine. So now we're going to decide, are those numbers the same? So how do we do that? You have 3 choices. You could reduce your fractions and see if they match. You can divide each one. No, there's only 2 choices. You could reduce the fractions or you could divide the numbers and use decimals. And that's what I did. When you divide, make sure your top is divided by the bottom. And that's 0.75. Try it out. Top divided by bottom is 0.75 as well, which is great. Top divided by bottom is again 0.75. Now, since all these values are the same, so my answer is, are the triangles similar? Yes. They are similar. Similar by what? It's this one. Similarity. Okay. And what else do we have to know? If so, write a similarity statement. Okay, we still have to do that. Similarity. Statement. So I'll start with one of them. It doesn't matter which one you pick. For this one, I'm going to reuse that where the letters are because I need those letters. So I'll start with the small one. It doesn't matter. You can start with this one, but I'm going to call it triangle ABC. So ABC, similar to triangle. And then I have to go here and decide AB would be EF, EF, G. Okay, so this is similarity statement. This is the reason, explain how you know. And this is why. Okay, so now let's look on the bottom. One more question. Determine whether the triangles are similar. Again, it's a yes or no answer. Yeah, yes, they are. No, they're not. If so, write a similarity statement and name the postulate or theorem you used. If not, explain. The postulates would be AA, SAS, or side, side, side. Those 3. Okay, let's look. We got one angle. That's good, but 2 sides. I know I have to use this one because we have one angle and the 2 sides that form that angle. They call it include. Yeah, so this is my goal. Now I have to set up the proportion to see if it actually works out. So let's start with this bigger triangle. I would say that 10 corresponds to 8. Yeah, 10 corresponds to 8. Then I have to go back here to this one and say 6 would correspond to 6. Well, that doesn't work because I know 6 over 6 is never the same as 10 over 8. Try it out. 6 over 6 is 1. 10 over 8 is 1 and 1.25. So nope, this doesn't work. So my answer is no. They are not similar. And then I have to say why, because they're asking this, if not explained, because the included sides do not form a proportion. So that would be an example of SAS, but unfortunately it doesn't work because the proportions of the side length are not equal, the ratios. Okay, next page, let's look. Nothing on the next. 364 is the next page I'm going to. That's this one, 364. And it's about indirect measurement, which is kind of interesting. Sometimes you can use similar triangles to find lengths that cannot be measured easily using a ruler or other measuring devices. So sometimes distances are just too big. So you can use indirect measurement . You can use indirect measurement to find lengths that are difficult to measure directly. One method of indirect measurements uses the fact, well, this one, I don't know, the light reflects on the mirror at the same angle at which it hits. We're not having an example of this, so I don't want to go into that. The example I'm going to show you is this lake problem. This is kind of pond, right? Well, you want to know how far across the pond is. It would be almost impossible to measure that with a tape measure, unless you have somebody that can throw the tape on the other side. So that would be a good example of indirect measurements. Explain why the triangles are similar. They are similar, I'll tell you why. Then find the distance represented by X. So we're looking for how far is it across the lake. So I see two angles that are equal. This one, and the other one are the vertical angles. So we have similar by Aaa postulate. So this little triangle here is the same shape as the big one. Does everybody understand that? And now we can write a proportion, correct? So now we have to set up a correct proportion. This is always the issue. That involves X, because we do want to find X. Involves or uses. So here's our X. All right, let's see. We got, so we have to find the corresponding sides, right? So how about X? Or let's start with this side. 120 over X, these two are corresponding, is equal to 90. So I started with 120, so I come back to this littler triangle and use that number over 135. Notice in my calculations, I do not use the measurement feet, okay? So now when you solve this, you use what's called cross product. You multiply across. So X times 90 is simply 90X. And 120 times 135 is, if you use a calculator, 16,200. Okay, come up here. I'm going to rewrite it. Divide by 90. Remember, x is the distance across the pond that we're looking for, right? So you can also do 1,620 divided by 9 because you can cancel any common zeros to make it shorter. And I believe x is 180. So this right here is now, we know that's 180 feet from here to here. But I'm still going to write a sentence about it. The distance across the lake is 180 feet. Okay, so that's an application of similar triangles, and the one down here is also very interesting. The Washington Monument. Oh, you know what? I want to see if I can find a photo of that. Yeah, so I found a photo. There it is. This is that famous monument in Washington. You'll see it if you watch Forrest Gump, has a scene there. So we're looking for the height of this monument. Okay, that's another way you can use indirect measurement with similar triangles to find the height of buildings by measuring their shadow. So let's look. At a certain time of the day, a 1.8 meter tall person standing next to the Washington Monument casts a 0.7 meter shadow. So the person and its shadow. At the same time, this is important because the sun has to be at the same angle because your shadow will change. The length of the shadow changes as time goes on, right? It gets shorter during noontime, longer at the end of the day. At the same time, the Washington Monument casts a 65.8 meter shadow. So that one is easier to measure. The shadow is easier to measure than the actual height of the building. How tall is the Washington Monument? So I'm going to draw this out so that we have your monument right here. So call it Washington Monument. We want to know how high it is. So I'll call that X, the height, yeah, from here to here. But we know that the monument casts a shadow at a certain time of 65.8 meters. And if I connect this here, then I have a triangle. So these lines are really not there. That's why they're dotted. So the sun kind of up here then, right? Shining, and there's the sun coming down. This is the shadow. This is the monument. Okay, makes sense? So now we have a little person or a big person. 1.8 meters is 6 feet. So this person is standing here. It's not to scale apparently, okay, because I can't draw this small tiny person. This person is 1.8 meters tall and casts a shadow of 0.7 meters. So there's our second triangle. These two triangles are similar. Why? Because we have that right angle here. We need one more, this angle, because it's the same time of the day. This angle and this angle would be the same. So now I have two angles that are equal, and that tells me the two triangles are similar. Okay, are you following so far? Now we're going to find X by set up a proportion. And I'm going to hopefully set it up correctly. You have to look for the corresponding parts. So when you set up involving X, so you want to have X somewhere. Somewhere in your equation you have X. So this is a proportion, two equal ratios. Let's start with X. So get that out of the way. So this length right here corresponds to this length, which is 1.8. And then this one, 65.8, is the shadow. So that corresponds to 0.7. Okay, notice I started here, went to here, came back here, over here. So this is a correct proportion. Now cross product, x times 0.7 is simply 0.7x. And then use your calculator, 1.8 times 65.8. And when you multiply that, you will get 118.44, correct? And then you divide by 0.7. I'm gonna come up here, use your calculator. There's a division problem. You get 169.2. So now we know that the height, x, is 169.2 meters. It's in meters. Notice when I do my math, I don't get bothered with units, but at the end I have to put it back. The Washington Monument is 169.2 meter tall. Make sure you have a decimal point here. And there you are. This is another good application, the shadow of a person compared to the shadow of a large object. Now homework, I'm going to have you circle those. You're going to do number 9. Read the questions. Are the triangles similar? It's a yes or no. Similarity statement and explain. So you have 3 choices, AA, SAS, or SSS. Okay. Number 10. Number 11, same thing. Oh, there's the Washington Monument again. And then we are page 366. Now on the top, vocabulary. How could you think of Washington Monument? Question. And then there's an error. Here's your picture over here. You need to figure out which proportion is correct, which one is not correct. There's one that's correct, and that, so you can just write incorrect, correct, whichever one it is. Then we're going to the next page. Number 15 on the top and number 17. And then number 23. That's it. Enough for you guys. See you later.